UCIe, Universal Chiplet Interconnect Express. UCIe packages are revolutionizing the semiconductor industry by enabling the integration of multiple chiplets into a single package. The UCIe spec document mentions two kinds of packages. Let's explore them in this session. CIE specification supports two main types of packaging technologies. The first one is standard package, the second one is advanced package. These packages differ primarily in terms of packaging technology, bandwidth, power efficiency, and target applications. So both package types share the same architecture and protocols, ensuring interoperability and flexibility in the design. In the upcoming slides, let's focus how this packaging technology is different for these two packages. Let's talk about flip chip technology now. See, we use bumps and C4, C2, again and again. Let's understand what are those things, right? So bumps are general term for conductive structures connecting chips or substrates. For example, in this case, right, this is a chip and this is a substrate. Okay, and these are bumps. Okay, so bumps are general term for conductive structures connecting chips or substrates. These are small conductive structures on the surface of the chip or substrate, here or here. Okay, that enable electrical connections between those two. They can be made of various materials, including solder, copper, and other metals. Okay, so again coming to the C4 is also again a bump. Okay, the solder bump we call it as. Now C4 stands for controlled collapse chip connection. This is a specific type of bump technology where solder bumps are formed on the chip surface. Then when the chip is flipped and placed on a substrate, we are talking about flip chip, right? So when the chip is flipped and placed on a substrate, this makes a connections by automatically collapsing, controlled collapse chip connection. That's what we call it as C4. Okay, next evolution is micro bumps, where it's a more advanced type of a bump, typically smaller and made of copper, used for higher density connections and performance. Okay, let's see how they are connected to the UCIe. Okay, so chip interconnection bump technology, if you summarize what I said, right, chip interconnection bump technology has progressed through three distinct generations. The first generation, we can say it as C4, that's solder bumps. Okay, they utilize high late solder bumps with a pitch exceeding 130 micrometer. So we C4 stands for controlled collapse chip connection. The multi-chip modules, 2D packaging, it's C4 technology is used in these things. Okay, the next evolution, next generation in packaging is we can call it as the second generation. That they use C2, chip connection stands for. Second generation introduced micro bumps with a pitch ranging from 40 to 130 micron. This technology is widely used in today's packaging technology. We can call it as chip connection C2 technology, or you can also call it as 2.5D. Okay. For example, the way the bumps size and pitch got reduced over a period, it's is in the image. Okay. In third generation, right, we also call it as 3D IC, achieved a significant reduction in bump pitch to below 30 microns. Okay, so enabling advanced 3D chip integration. Okay. Now that we know, UCIe talks about two packages. One is standard package, other one is advanced package. So the type of package, standard or advanced, right, significantly influences the use of C4 bumps and micro bumps. Okay, let's see what is the difference between these two packages in terms of bumps. Okay, just to visualize, I'm using an image here. So the bumps are like the electrical connections between the substrate and the chip, right? So they're like balls only, solder balls or solder bumps, right? So the distance between the midpoint center of two bumps neighborhood, right? That is bump pitch, and generally it is fixed. Okay. We also have in this diagram, right? We have a connection from pad to the bump. So the red color we call it as redistribution layer or RDL. Okay. So that is shown in this diagram. Okay. See, this bump either can be C4 or C2, but RDL is what I'm showing here. Okay. So now this is a diagram of a C4 bump, the third one, right? So C4 stands for the controlled collapse chip connection. Okay, the standard package uses this solder bumps or C4 bumps. Okay, they provide a reliable and cost-effective method for connecting chips to the substrates. So because since the bump pitch is bigger compared to the C4, and then we can relatively say interconnect density is lower for C4 bumps compared to C2. Okay, so the advanced package, UCIe advanced package, it uses microbumps. Okay, and microbumps are essential for achieving the higher interconnect density and performance required for advanced packages. Since this bump size and bump pitch is smaller for microbumps, we can say interconnect density is higher. And hence for typically the standard package we use 16 lanes, whereas it comes to advanced package we go for 64 lanes. So what enables it is this micro bump size as well as the C4 bump size. So this is the next image micro bump. Only thing is this size is smaller. Okay, whereas C2 stands for chip connection. Let's revisit the UCIe packages as mentioned in UCIe spec document. Okay, UCIe, as I mentioned earlier, it has got two packages. Uh, Standard packaging, and it comes with advanced packaging technology. Okay, standard packaging technology, advanced packaging technology. Standard packaging technology uses traces on organic package or substrate. For example, in this image, right, the green colored one is a substrate. So it uses it uses the traces to connect near it dies. Okay. In the advanced packaging, right, we got they are realized using multiple technologies. I'm covering three of them. In the first one, right, we have a silicon bridge. Okay, used for connecting the neighborhood dies, of course, definitely on the substrate itself. Okay, in this example too, we still have a substrate, but we have an interposer, okay, used for connecting the two dies. In the third example, we still have a substrate, but we have a the fan out organic interposer now become organic interposer with additional feature of fan out. So fan out organic interposer here. Okay, these are three examples of the UCIe advanced UCIe package. So let's talk about 2D. See, standard package generally we can call it as a 2D packaging, whereas advanced package we can call it as a 2.5D packaging. 3D, the UCIe package does not talk about 3D packaging. Okay, so standard packaging, used for low cost, long reach interconnects. Here it supports 10 mm, the card is short, 10 mm reach as well as the 25 mm, the reach. So when it comes to reach, the meaning here is the distance between the two dies, because we need to transfer high speed signals between the two dies, right? So what is the distance between two dies? That is, it supports 10 mm, it supports 25. Generally we call them as a long reach. 10 mm is short reach, and 25 mm is long reach. Whereas advanced package, right, the channel reach is short, so it is lesser than 2 mm. Standard packaging, though it has a C4 bump which is quite bigger, bump size is smaller, and we have it's aimed at long reach, 10 mm to 25 mm interconnect. It still provides a significantly better BER characteristics compared to off-package SerDes. Still, we have an advantage here. Okay. Let's come to the advanced packaging technology. This interconnect is expected to be optimized for high bandwidth and low latency, with best performance and power efficiency characteristics. Naturally, the bumps we are using is micro bumps with smaller, bump size and bump pitch. At the same time, the channel reach is also smaller, much smaller, lesser than 2 mm. So that is the reason we are able to achieve higher density and big number of lanes. At the same time, high speed, high bandwidth. So little detail into the packaging technologies. What you're seeing is a standard package. You see standard package where your die 0, die 1 and die 2 are sitting directly on the substrate, and dies are connected through the uh, and connections are passing through the package substrate. Okay, of course TSVs are used there. Okay, now let's get into the advanced package. See, we saw that there are ways of connecting the dies. People connect in different ways, the two dies in advanced packaging, right? Let's go one by one of them. So first one is the interposer. Okay, in this case, what is interposer? As you can see here, example, earlier in the standard package, my dies were sitting directly on the substrate. In this case, my dies are sitting on the interposer, this one. My dies are sitting on the interposer. Okay, and this interposer is silicon. Okay, this, and what is this interposer? We can call it as a substrate for chiplet interconnection. Of course, it is acting as a substrate for chiplet interconnection. See, this is interconnection happening, and these interconnections are happening through the on the this substrate, right? We can call it a substrate for chiplet interconnection. So a separate silicon substrate with through silicon vias, TSVs. How interconnection happens? Through TSVs. TSVs are bigger or longer vias. Okay, see, vias connecting M1 and M2, right? These are longer vias. Okay, so this interconnection between two diodes happens through TSVs. Of course, TSVs are generally vertical, but here in this case vertical and horizontal also, like connection is also happening here. So COWS, again it's a kind of interposer based one, we can say that. In this case, so silicon substrate is a silicon wafer, and we call this as a chip on wafer on substrate. Okay, so multiple chips on an interval. On an interposer we have multiple chips. Okay, basically the packaging happens on the wafer here. First packaging happens on the wafer, then the individual dies are diced out, right? So we have a multiple chips on an interposer. So this technology combines a silicon interposer with a fan-out packaging process. What is fan-out? Fan-out is, say, fan-out packaging is typically refers to a process where the chips I/O pads, the pads, are redistributed onto a larger substrate. Okay, through RDLs, redistribution layers, often using a fan-out shape. Okay, this allows for better heat dissipation and electrical performance, because we have space between the two pads, right, two routings, right, we have a better heat dissipation and electrical performance and ends. Okay, so COWS, okay, chip on wafer on substrate, this concept, right, is a step further, compared to the interposer, using silicon interposer as a substrate, enabling higher integration and performance. Okay, let's go for next one. We call it as a silicon bridge. Okay, so again in this case the substrate is made of silicon. Okay, this is an example here. Okay, so the dies are sitting on the, you can see this here, right? The dies, all dies are very similar to the standard package. Dies are sitting on the package substrate, whereas interconnection is happening through this silicon bridge. Okay, okay, this interposer is made up of silicon, and what is this is the structure is a small silicon die. This blue colored one is a small silicon die with embedded routing layers. These routing layers, these things, they are embedded into the silicon die. Okay, what are the advantages? It has got a low parasitics, it has got a higher bandwidth because they're custom route, yeah. Custom, this is silicon bridge is custom built for interconnection and die-to-die connection, right? So one of the example of silicon bridge or evolution, we can say that, is EMIB. So what is this EMIB? Is embedded multi-die interconnect bridge. Okay, so this description is it's a silicon bridge with embedded routing, very similar to the silicon bridge. See a little evolution. Okay, see evolution. A silicon substrate with multiple layers of embedded metal interconnects. Advantages is very high density, improved high signal integrity. And the third one, right, is fan out organic interposer. So in the first case itself, we use interposer. In this case, instead of silicon interposer, we are using an organic interposer with an additional feature of fan out. Okay, then what is this fan out? We already seen chip IO pads are redistributed to a larger substrate for a better heat distribution and electrical performance, right? So RDL layer is used here. So where this RDL layer is used? In the die, for example, in this case die 0 is used. Okay, so this and this are exactly same. Okay, extra feature is this this one interposer is now organic. Second thing is that we have a silicon bridge in this case. It's a combination of this and this. Okay, this and this combination. Okay, so we have a silicon bridge from this type. We have got a interposer from this type, organic interposer. Okay, so what is the advantages? Lower cost, suitable for low density applications. And what do you mean by die? See, this die as fan out feature, RDLs, for distributing the pad connections. One of the FOCOS, fan out chip on substrate embedded bridge, is one of the example of fan out organic interposer. Let's look into some of the characteristics of two UCIe packages. Let's make it clear now. UCIe 1.1 and 1.2 talks about standard package and advanced package. That is, UCIe 1.2 talks about 2D package and 2.5D package, but it does not talk about 3D packaging. Whereas UCIe 2.0 talks about 3D packaging. Okay, in this case I'm only covering two packages. Okay, 2D and 2.5D. So the supported speeds per lane in both the packages is up to 32 giga transfers per second, but minimum support is 4 giga transfers per second. It must support it. Okay, both packages, it's 32 giga transfers per second is the maximum it supports. Okay, bump pitch. See, as I mentioned, right, the 2D package or standard package uses C4 bumps, where the bump size is bigger, bump pitch is bigger compared to 2.5D microbumps, right? So what is the bump pitch in this case is 100 microns to 130 microns, whereas advanced package or 2.5D uses the microbumps. We can also call it as copper pillars, whose bump pitch is 25 microns to 55 microns. So bump pitch is what? It is a center to center distance between the adjacent bumps on a chip substrate, which is anyway fixed. Okay, it's a critical parameter in determining the overall density of interconnections in a package. This is exactly the reason standard package allows 16 lanes, whereas advanced package allows up to 64 lanes. Because we have a micro bumps, we can have it allows more density. Okay, more interconnections. Channel reach. So we have standard package supports both short reach as well as long reach. The short reach it supports is up 10 mm. The long reach it supports is up to 25 mm. Okay, what is this reach? Is that it's a maximum distance over which high speed signals can be reliably transmitted between chiplets within a package. Okay, so when it comes to advanced package does not support long reach. It only supports the short reach, which is 2 mm, which is much smaller than what is supported in the short standard package, right? um, right. Why advanced package? The aim advanced package 2.5D UCIe advanced package, right? It aims at better performance and better bandwidth. Naturally, the interconnect parameters has to be optimized. You know, so hence it supports the smaller reach. Okay, now till now we compared the two packaging types. So because of this, lot many differences arises between standard and packaging. For example, the architecture might slightly change. For example, 16 lanes versus 64 lanes. The power efficiency will change. The bandwidth supported will change. Architecture here and there it goes a little bit change, right? Applications also goes change, right? This we will see it in next sessions. Thank you very much for your time.